In this how-to video, you'll learn how to solve a system of linear equations. Slide 2 talks about just what a system is and solutions. Slides 3, 4, and 5 talks about the specific methods that you can use to solve a system, so solving by graphing, substitution, or elimination. And slides 6 and 7 talk specifically about systems that have no solutions or an infinite number of solutions. Feel free to watch the whole video or jump to the slide that you need. A system of equations is two or more, could be 3 or 4 equations in the same variables. So down here would be an example of a system of equations. The purple equation has both x and y, and the blue equation has both x and y. So we have two equations that are comparing the same thing. The real-world application of this might mean that you're comparing total cost at, say, 2 cable companies, that would be your y-axis, to maybe the number of months that you have that service. So that's why the same variables are important, because you want to make sure you're comparing total cost to number of months in both cases. You wouldn't want to compare one to months and then the other to years. One way to check if an ordered pair is a solution to a system is to just plug it in and see if it works. So if you replace x with 0, negative 2 times 0 would be 0, and then plus y, which is 1, would be 1. It comes out to 1. So yes, it's a solution to the purple, but in order to be a solution to the system, it has to be a solution to both. So then I'd also have to check it for blue, so I'd replace x with 0 and y with 1, and if I do out the math, I get 2 equals 2. So since it was a yes to both, then yes, it's a solution to the system. If it was a yes to the purple but a no to the blue, it would be not a solution to the system. Remember that solutions to linear equations are points on the line, so you can see that the blue line is made up of an infinite number of points, its own points, and the purple line is made up of an infinite number of its own points. And you can actually see that 0, 1 is the point of intersection. So when you find the solution to a system of equations on a graph, what you're really finding is where two lines intersect. So the solution here is 0, 1. To solve a system of equation by graphing, the first thing that you're going to do is graph each of the lines. So since this line is already in slope-intercept form, I'm going to use slope-intercept form to graph it. So it has a y-intercept of negative 2 and a slope of 3. And I'm going to graph multiple points in the hopes that one of them would become my point of intersection. Bring this down here. So that's my purple line. And then for my blue line, since it's in standard form, I could put it in slope-intercept form, but I can see that the x and y intercepts are pretty easy. Remember, to find x and y intercepts, you just replace the opposite coordinate with 0. So if y was 0, 4 divided by 2, x would be 2. And if you replace x with 0, the y-intercept also happens to be 2. And so then I'm going to connect these with a line. And when you're doing this, it's really important that you use a ruler, otherwise you might not get an exact answer. And you can see that my solution looks like it would be the point 1, 1, because that's the point of intersection. Now I could check that by actually replacing, so x with 1, 3 times 1 is 3, minus 2 is 1, which is what we want. 2 times 1 is 2, 2 times 1 is 2, 2 plus 2 is 4, so it works in both, so I know that that's my solution. So solving by substitution is just another way to solve a system. You could solve it graphically, or you can substitute. So the first step of substitution is to make sure, or it's the idea of replacing. So this equation, since y is isolated, this says everywhere you see a y, which in this equation I do, I can replace it with x plus 4. So in this equation down here, I'm going to take out the y, and I'll kind of move it off to the side, and move that over, and I'm going to replace that with x plus 4, because this says y is equal to x plus 4. So that's why I'm allowed to kind of slide that in. Now I'm also going to need to use parentheses, because this 3 here was multiplying this entire y. So anytime you substitute, you want to use parentheses. So now I'm just going to solve like a normal one-step equation. So I would start by distributing 3 to x and 3 to 4, and then combine like terms. So I get 5x plus 12 equals 32. If I subtract 12 from both sides, I get 5x equals 20, and then x equals 4. But I only have half of my answer so far, because remember, answers to systems of equations or solutions are ordered pairs. So I have my x coordinate, I still need that missing y coordinate. So I'm going to take this x value and I'm going to plug it right in here. So then y would be 4 plus 4, which is 8. And again, you could check by replacing in both of the original equations. I could replace x with 4 and y with 8 and make sure it comes out. Now in this example over here, since one of my variables isn't isolated, I'm not ready to substitute. So I have to isolate one of my variables. It could be x, y, y, or x. And I want to choose the easiest one possible. So this equation would let me isolate x in one step by subtracting 2y from both sides. So I'm going to show this down here. So x would equal 4 minus 2y, because I could subtract 2y and subtract 2y to isolate x. Now I have an equation that says everywhere I see an x, which I do, I can replace it with 4 minus 2y. So I'm going to take this equation, I'm going to rewrite it, 4y minus, but then instead of writing x, I'm going to write this quantity right here. I'm also going to be extra sure to use parentheses, because as you'll see, this negative sign, this minus sign, is being applied to every component of x. So bring down my 4y, distribute that negative. Negative distributed to a negative is going to become plus. And now I have a multi-step equation. So I get, if I combine like terms, 4y and 2y gets me 6y. And just to save time, I'm also going to bring this negative 4 over by adding it to get 24. Divide both sides by 6, y equals 4. And I'm not done yet because that's only my y coordinate. So if I take this y equals 4 and plug it in right here, then that means that x would equal 4 minus 2 times y, but I just found y, which is 4, and that would become 4 minus 8, which is negative 4. So another method that you could use to solve is by elimination. There's going to be 3 examples. I'm just going to make these smaller. And when you're eliminating, your objective is to get one of your variables to cancel out. So you can see with my 3x's that if you add these equations together, draw a line. If I add these equations together, 3x plus negative 3x would cancel, it would be 0. 2y plus 5y would be 7y, and 9 plus 5 would be 14. Now I have a really easy equation, and I get y equals 2. So I have 1/2 of my answer. I know that the y coordinate is 2. So I'm going to go back and plug that up here. So I get 3x plus 2 times y, but we just found y to be 2, so that would be 4 equals 9. And then I would subtract 4 from both sides, so I get 3x equals 5. And then if I divide by 3, I get x is 5/3. And it's okay that's a fraction. Obviously not a great answer, but it is a possibility. On the next equation, it's a little bit different because you can see that instead of things being lined up, you have minus signs on top of equal signs. So we want to get these equations to be stacked, so that way we can eliminate. So the top equation's in standard form, and elimination tends to be a little bit easier in standard form. So I'm going to keep this top equation, so I'm just going to rewrite it. 4x minus 2y equals 10. And I'm going to put this equation, so it's in standard form, by moving x and y on the same side, and that would become 8x minus 2y equals negative 6. So now everything's nice and lined up. And since I have negative 2y, keep in mind that negative is there, and a negative 2y, if I added them, that would be negative 4y. So I'm going to subtract, because a negative 2 minus a negative 2 would be plus positive, and that would cancel. So I'm going to minus. So then 4x minus 8x would give me negative 4x, and 10 minus negative 6, be careful with that, minus the negative, would be 16. Don't forget that negative 2y minus negative 2y canceled, that's why y is gone. Divide both sides by negative 4, and x would equal negative 4. So you only have half of your answer. You still need your y coordinate, so I'm just going to plug that in right up here. So 4 times x, which we just got to be negative 4, would be negative 16 minus 2y equals 10. If I add 16 to both sides, I get negative 2y equals 26, which will give me a y coordinate of negative 13. And then on this last example, you can see that if you add 2x and 5x would be 7x, and if you subtract, it would be negative 3x, so that wouldn't cancel. And if you add your y's, you get 5y, and if you subtract, you get 1y, so that wouldn't cancel. So what I need to do is figure out what number can I make match, so that way I can add or subtract. It's kind of like finding a common denominator. So I'm going to make my x's match, and the number that I can think of that I can get both x's to be would be 10. And I can do that by multiplying the top equation by 5 and the bottom equation by 2. Sometimes, just like when you're adding fractions, you don't have to multiply both equations. Sometimes you just have to multiply one and then they'll match. But in this case, I had to multiply both. So I'm going to end up with 10x plus 15y equals 20. Make sure you're multiplying every single component by that 5 all the way through. And then on the bottom, I'm going to get 10x plus 4y equals negative 2. Keep in mind, I also could have multiplied by 2 to make the y a 6 and by 3 to make the y a 6. That would have been another option. And so now that I have two 10x's, I'm going to subtract, because 10x minus 10x would cancel. 15y minus 4y would be 11y. And then 20 minus negative 2, pay attention to that minus negative, it becomes plus positive, would be 22, which gives me a y coordinate of 2. So I have half of my answer. And I'm going to plug that back in over here, only because these equations have bigger numbers. I can really plug it into any of the 4. I'm going to plug it in to this one. So I'm going to get 5x plus 2 times y, which was 2, so that's 4, equals negative 1. If you subtract 4 from both sides, you get negative 5, and if you divide both sides by 5, you get negative 1. So final answer of 1, negative, or negative 1, 2. Keep in mind that any of these systems on slides 3, 4, and 5, we've talked specifically about a certain style of solving, but had I graphed any of these equations, I would get the same solution. Had I substituted, I'd get the same solution. So you want to use the method in real life that would make the most sense. If they're stacked and in standard form, it's probably going to be elimination. If one of your variables is already isolated, it would probably be substitution. And graphing usually takes the longest, but it's the best visually, so graphing is usually people's last choice. So if you remember back in solving equations, when you solved an equation, your goal was to isolate the variable. And sometimes in doing that, you'd either get a regular solution like x equals 5, or sometimes you get like 3 equals 7, which meant no solution, or maybe 3 equals 3, which back then meant all real numbers. So similar things are going to happen with systems. So let's take a look at this first system right here. So because they're in standard form and stacked up, I'm going to use elimination. And to do that, I'm going to need to multiply the bottom equation by 3 to get it to match. So my top equation right here, I'm just going to rewrite 6y minus 3x equals 12. And my second equation, if I multiply everything by 3, I get 6y minus 3x equals 18. And to eliminate, I need to subtract. So 6y minus 6y cancels. Negative 3y minus negative 3x minus negative 3x would also cancel. But when they cancel, don't forget they're becoming 0. So I'm actually left with 0 on the left side of my equal sign. Always bring that equal sign straight down. You need something on both sides. And then 12 minus 18 would be negative 6. Since 0 doesn't equal negative 6, just like back in solving equations, that would mean no solution. On a graph, what that would look like, just to give you a quick picture, remember if the solution is where the lines intersect, and this system has no solution, that would just mean that the lines must be parallel. And I'm just doing a very rough sketch of what I think these lines would look like. I'm not doing it accurately. But they would be parallel lines, because parallel lines never intersect, therefore there's no solution. So now in the second example, since y is already isolated, this says that everywhere I see a y, which I do, I can replace it with 3x minus 2. So I'm going to use substitution. So I'm going to rewrite my second equation, 9x minus 3 times y, but instead of y, I'm going to put in that 3x minus 2. And now I'm going to solve this like a normal equation by distributing, making sure it's negative, and negative 3. So minus 9x plus 6, and that's because negative 3 times negative 2 would be plus 6, equals 6. 9x minus 9x is 0, so I'm left with 6 equals 6. So back in chapter 3, we used to say all real numbers, but if you picture this on a graph now, what that actually means is that you have two lines. So we have this blue line, which might look something like this, and then you have this green line, which is actually the exact same line. So we're not going to say all real numbers anymore, because all real numbers means that you can pick anything you want, and if you just look, the origin, for example, isn't on these lines. So all real numbers to me would mean pick anything you want in the entire coordinate plane. Now the difference is these two lines have infinite points in common. So we're going to say infinite solutions because that's how many solutions they have. But we can't pick anything that we want because like this ordered pair over here, for example, doesn't work, or this one. But they have infinite points in common, so we say infinite solutions. So the last thing that we can do with the system is without solving it, which means don't graph, don't substitute, don't eliminate. You don't actually have to find the solution what it is. Without solving it, just determine how many solutions are there. So if we kind of work backwards on this picture, you know that a system will have no solution if they're parallel lines. So parallel lines, now if I kind of work forward, parallel lines have the same slope but different y-intercepts. I know that it's going to have infinite solutions if they're the exact same line, which would mean they have the same slope and the same y-intercept. Which means that if their slopes are different, as soon as their slopes are different, they're going to intersect at some point, which means since all lines are straight, they're going to intersect once. So you can see on this picture, you need to know about the slope and the y-intercepts. So if I look at this first example, I know because it's in slope-intercept form, which it is because y is isolated, I know that the slope is 5 and the y-intercept is -3. For this second example, it's not in slope-intercept form, so if I want to know the slope and the y-intercept, I'm going to have to get it there. So I have 2y equals 6 plus 10x. If I divide by 2, I end up with y equals 3 plus 5x. So I have a slope of 5 and a y-intercept of 3. So if I work through this chart, I start here and I look at my slopes. My slope is 5, my slope is 5, they're the same. Then I look at my y-intercept, -3 and 3. They're different, which means there's no solution. These two lines are parallel because they have the same slope but different y-intercepts. So you can go through this process for any system of equations and determine if there's infinite, no, or one solution.